Yeah, thanks for the introduction, and it's my pleasure to be back here to talk about some of my thesis work and be interviewed here for the postdoc position. So today I'm going to talk about a part of my thesis work on differentially private machine learning. So before I delve into this specific aspect, I'd like to give a quick summary of the other part of my thesis work. So I've done work in both classical statistics problems like nonparametric regression, by pushing the boundaries of existing literature and deriving like minimax optimal methods for doing things like doing nonparametric regression in a locally adaptive fashion. And I've also worked on developing a couple of the new learning paradigms, like learning with privacy constraints, and in particular, differential privacy constraints. There are a related line of work called adaptive data analysis. That's something that tries to deal with p-hacking, the problem of p-hacking and false discoveries in science in a more formal fashion. So there are a couple of other things that I worked on. So I'm not going to talk about anything except for learning with differential privacy and other privacy constraints. Sorry. But in case you are meeting with me one-on-one, like feel free to bring up anything that's common in our interest so that we can have a chat on it as well. So let's get it started. So here's what I'm going to do today. I'm gonna motivate the problem and quickly talk about differential privacy. This is just to get everybody on the same page. So if you are already familiar with differential privacy, just take it as a quick refresher. Then I'm gonna talk about two of the technical work that I've done on the problem of differentially private machine learning and how the results motivated us to consider a weaker but practically more relevant notion of privacy called On-Avg-KL privacy. And I'll end the talk by describing a few ideas for the future along this line of work. And hopefully that will connect back to some of the other things that I worked on. So in the big data era, a lot of companies and also the public sectors are collecting personal data. They're collecting this data for various purposes, including making better product, making more personalized recommendation engines, and so on and so forth. So all these use of personal data, they tend to make our life easier since people have more and more presence digitally online. The amount of data that people are collecting are also exploding in every aspect. So all these data can also be used to solve some of the persisting social problems that we're facing, like killing energy, food safety, and also to design like better medical care and better and more personalized education systems and so on and so forth. And more than a century of research in statistics and several decades of research in machine learning has given us an entire array of methods to tackle this problem as long as the data is available. Since but there's just one catch. With the increasing awareness of the privacy issues in the public and the pending more stringent legislation on privacy and data sharing, it just becomes harder and harder to get data to make use of these amazing methods to address some of the pressing problems that we're facing, and hence makes the world a better place. So it simply becomes harder to get personal data, especially in the sensitive domain, like medical domain. All right. So these concerns are not ungrounded. Thanks to a couple of recent incidences of privacy breaches. For instance, the Netflix prize, the second Netflix prize has been canceled. This is like the competition for building better movie recommendation systems. like the second Netflix prize had been canceled due to in response to a lawsuit related to privacy concern, and more recently, New York City released its taxi data. Like some of you might have worked on this already. And the moment that the data get released, it immediately get hacked, and people build a one-to-one mapping from the hashed keys to the corresponding license plate. So now, like on this from this data set, you can identify every individual taxi trip with its corresponding driver's license of the taxi driver. So it's a really serious loss of privacy from the data set. So all these incidences highlight the need for formal methods with provable privacy guarantees, and it also highlights the need of new ways for data analysts to interact with the data sets, because like it's clearly hard to release the entire data set without losing much information regarding individual level privacy. So previously, there had been many approaches that have been proposed to deal with these problems, including decades ago, data swapping. Like this is still used in US Census, and there are a whole area of research called statistical disclosure control, and then there's k-anonymity. So most of these methods aims at removing or somehow modifying the personal identifiable information before releasing the data set. But in the high-dimensional data set, especially when the data is a behavioral data of people's activities online, it's harder to draw the line between what is personal identifiable information and what is not. In the specific case of this Netflix challenge, what happened was that Vitaly and his students from Cornell, they tried to use an external data set from IMDb and then just match the individual records from the anonymized version of the Netflix data to the public data at IMDb, and they show that they can do this successfully with high probability. So with additional site information that's available to the attacker, it becomes much harder to protect privacy with these sometimes heuristic approaches. And in the big data era, such information is much easier to get than before. Okay, so then there comes differential privacy, and differential privacy's take on this problem is that now we're not making any assumptions on the kind of information that are available to the adversary who tries to identify users in the dataset. But instead of allowing the adversary to have access to the dataset directly, we need to come up with a data curator that tries to insulate between the data and the adversary. And the adversary can only access the data through framing some kind of questions, and the curator is supposed to come up with an answer to that questions with a little bit of randomizations in it, so that he's not releasing information about individual data while still answering the question relatively accurately. So this is a setting that differential privacy is trying to achieve. So it's like still a little bit abstract for the moment, especially on the problem of site information. So I'd like to just illustrate differential privacy through this simple example of who likes Justin Bieber. Okay, so Alec he started a special interest group in pop music yesterday in New York City lab, and everybody gets so excited about it and all enrolled into this special interest group. And the first day, Alec did a poll, and do you like Justin Bieber? So everyone answers this question honestly and anonymously. At the end of the day, a total there are a total of 30 people who said yes to this question. So this comes as a surprise to most people because we didn't realize that there are so many Justin Bieber fans in New York City lab. I mean, yeah, but this is what it is. Like from this number 30. Aha. Yeah, including the interns and postdocs. So just from this number alone, like it's hard to figure out whether any individual actually likes Justin Bieber or not. So today I came in as a visitor, and Alec is kind enough to allow me to participate in this special interest group. So I did, and we repeated the same poll again anonymously, and everybody voted. Like let's assume that everybody answered honestly about the question, just like yesterday, and the result becomes 31. Okay, so even though we are only still only releasing just this aggregate statistic, but to my surprise, now my dirty little secret that I'm actually a fan of Justin Bieber is now known to everybody in New York City lab. Okay. So in this example, the given site information that's available to everybody here, but not me, is that yesterday it was 30, and I joined today. So I'm the only difference from the two polls. Okay. So this example highlights that given site information, the problem of privacy becomes a much harder one. And this might sound like a very amusing example of music taste, but it could be something that's very serious. Say if it's instead of a poll of Justin Bieber, suppose it's a study of financial transactions or a study of sexual assaults on campus, just identification alone can cause troubles for people who participate in this data set. Okay. So how would differential privacy resolve this issue? So it's a very simple idea. So what differential privacy does is that it randomizes the output of this summary statistics. So in other words, it just adds the noise to the number 30 and 31 in the two occasions, such that suppose I see that the answer is, say, happens to be 31, it becomes almost equally likely that the outcomes come from a data set where I answered yes and another data set where I answered no. Okay, so with this randomization, it becomes hard. This serves to obfuscate the potential inferences condition on the output, so that it offers a degree of plausible deniability. And for those who are familiar with statistics, this poses fundamental difficulties for any classifiers or any hypothesis test to tell between the two data generating distribution. Sid?
So it's really protecting this individual.
Yes.
Right? So it's not, for example, protecting against the fact that I can basically conclude that most people like Justin Bieber.
No, it's on the contrary, it tries to release it tries to be as accurate as possible on answering these questions regarding aggregates.
So there could be like a few people who don't like it, but like everyone has some kind of plausible deniability.
Yeah. But there's no way you can tell for sure any individual. That's actually the key point, that you can do this and still get something that's close to the true answer, but at the same time you prevent any kind of harm to comes to any individual in the data set. Okay, so all right, formally, here's a definition of differential privacy. So let Z and Z prime be two data sets that of people, and each one is a row. So let these two data sets that differs by only one row, and if and let's say A is a randomized algorithm that outputs something we call H, given a data set. We say A is epsilon differentially private if the log likelihood ratio of of this output of A giving any two adjacent data sets is uniformly smaller by epsilon. I'd like to highlight this point that this is for any two data set, and this is for all possible output H. So there's actually a 2 supremum in front of this log likelihood ratio. So it is a very strong form of protection and also a very strong type of requirement on this algorithm. So people decide that maybe we can weaken it a little bit by allowing a small failure probability delta. So if this event happens with a tiny probability, then we can tolerate that. So this is what we call the epsilon delta differential privacy. Okay, there are a couple of there are many algorithms for differential privacy. I'm just going to skip them, but I like to mention 3 convenient properties of differential privacy that makes it appealing to people who tries to get theoretical results out of this. So first of all, it features group composition. So like Sid just pointed out, this is only protecting an individual level of privacy. But suppose you have a small group of K, and you want to jointly protect all of them, any group of K, then if A is epsilon differentially private, then this same algorithm is also K epsilon differentially private to protect the small group of K. And then there's this adaptive composition. So suppose you have multiple access to the data set. Say A is one algorithm that's epsilon differentially private. So conditioned on the output of A, you come up with another way to analyze the data set, and that's what we call B because it's conditioned on output of A. So it's adaptive. And suppose B is also epsilon differentially private, then jointly the output of A and B is 2 epsilon differentially private. And lastly, it is close to post-processing. So suppose anything is output of a differentially private algorithm, any subsequent processing of the output will not break differential privacy. This is more of an information processing equality type of result. All right. So that's a quick short tutorial on differential privacy. I'm gonna now move on to talking about differentially private machine learning. But if you have any questions now, okay. Hopefully everything's clear so far. All right. So the setting of differentially private machine learning is like this. This is like the standard diagram for any machine learning pipeline. You collect the data, and then you pass it into a learning algorithm, and this learning algorithm would output some kind of hypothesis or classifier or prediction functions, like for you to use and release and deploy it in a web service. So previously, what people had been doing is to somehow privatize the data set before just feeding it to the standard learning algorithm and then come up with an answer. That has its advantage, but I claim that it's much more useful. It gives you much more accuracy, suppose you do it the other way around, by using a randomized learning algorithm so that you output a hypothesis that's random. And the requirement of differentially private machine learning is that this randomization in the space of this prediction functions needs to satisfy differential privacy. So since now H is not in the discrete domain, the requirement is that for any measurable set within the output domain, this log likelihood ratio of that needs to be bounded from above by epsilon. When the data for any two possible input data sets that differs by only one row. Just to make it more concrete, let's consider this example of recommendation system. So maybe this is just a model-based.
There was a soup over S in the previous in the definition.
Yes, it's a soup over H. Suppose H is a discrete domain. Yeah.
Oh, I see.
Yeah, then it's equivalent. Yeah.
So I guess the protocol that you're now imagining is that. So let's say there is a party that has the data.
Yeah.
Then the party is the one that the party holding the data is the one that runs the machine learning algorithm and then releases the output.
Right. Yeah. Yeah, that's exactly the setting. So here, this data Z is just movie ratings from all the users of Netflix, and this A is this training algorithm that Netflix is using to come up with a really nice movie recommender H. So now they can just deploy this H, so everyone who uses their service can just plug in their own data and get a prediction that hopefully would predict what are the kind of movies that they would enjoy. So the setting is that we now trust the data collector and the service provider, so Netflix can do whatever they want with the data, but the output, so this is whatever they release on the internet, is available to the adversaries. So other users might use this H and to try to somehow infer whether any individual users are in this data set or not. Okay, so the nice thing about this is that if you use a private learning algorithm to train this model, then prediction is considered post-processing. So no matter how adversaries would like Mongo with this predictor, he's not able to discover anything about individuals in this training data set. I hope this convinces you that this is a practical relevant setting of general interest.
This applies even if you crack open the predictor?
Yeah, even if you crack open the predictors and look at the internal states of that with any X plugged in, you will not be able to identify individual users in this training data set.
So I guess there is a little bit of trade-off, right? If I knew that, for instance, I'm only ever going to make, ever going to evaluate this classifier, say, 10 times.
Yeah.
Then I'm probably better off actually making the predictions private rather than
Yep.
the whole
Yep.
classifier
Yep.
private.
Yeah. 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 The same trade-off would go to this part. Suppose you privatize the data, then you can now fit any algorithms afterwards. So there's a little bit of trade-off in the kind of model that we consider. But this is like what we studied in this line of work. Sid?
Can you relax this requirement that you trust the service provider? What if you did some kind of, I don't know, verified computation thing, you gave it to someone, and that you could verify that their computation on the data actually was computing these randomized machine learning algorithms? Would that be okay?
Yeah, that's also okay. Like suppose there are a trusted third party who's holding the data, and Netflix say, okay, let me send you a request to train this model for me. I developed this model, and all Netflix would ever wanted is this H and perhaps some evaluations of how well this model performs. Yeah.
So in this kind of setting, if New York City wants to release its taxi
Yeah.
data, they don't release the taxi data. They make some brokerage service that people are gonna
Right.
train this for me, and
Right.
they send back
Right.
H.
Yeah. I'll get back to it. So there are other ways to release the data in forms of histograms, and you can release a histogram in a private fashion, and then it's up to you to do any form of post-processing to try to squeeze more accuracy out of it. So that actually connects to the non-parametric regression work that I've done. Yeah. So that will come at the very end. So after all this. So before I get to anything further, I'd like to just highlight this high-level connections between learning and privacy. So suppose we just try to classify these dots. These are classification algorithms for cats and dogs with features, weight, and height. And suppose we use this simple linear classifier, and we tend to just underfit this data set. And this output, the linear classifier, is a parsimonious representation of the decision boundary. So from the very, very high level, like this compression of the data set, like suppresses the private information. So I argue that this is more private than suppose you use a much more complicated algorithm to train it and then release H. Like in other words, like suppose you train a neural network or kernel-based method without the appropriate regularization, then we actually say this. We say that the model that you trained actually memorized the entire data sets. So that terms alone would remind you that H might contain like information about individual data points in this data set. So that's not private. So this this connection has been long known in the differential privacy community. So it's now well known that differential privacy implies a generalization. More formally, if a learning algorithm is epsilon differentially private, then A also has generalization error of at least epsilon. Okay, so in this case, the general definition of generalization is the expectation of the absolute value of the actual risk of your learned hypothesis minus empirical risk. So I'll make this more formal later with definitions of what's a risk and what's the empirical risk. But like this is known a long time ago. Like it dates back to it's a version of proving generalization through the stability argument, through the algorithmic stability argument. So knowledge of this result dates back to decades-old conversations in the early days of differential privacy between Frank McSherry and Adam Smith. But it's only more recently formalized in a lot of different settings, including the settings for adaptive data analysis, and we were also one of the first groups to realize this and apply this to the study of learnability. So I'll get to it shortly. So the first question that we try to address for this differentially private machine learning problem is what exactly can we learn privately? So this is a fundamental question in that suppose we ignore the sample complexity, and for every learning problem separately, we let n go to infinity. This is a yes and no question, right? So whether a problem is learnable or is not learnable, whether there exists a private algorithm that actually learns this model. So this line of this question was first addressed in 2008 by Adam Smith's group for the setting of pack learning. So this is a more restricted pack learning setting that considers only binary classification in discrete domain. All right. So we consider a slightly more general setting called Vapnik's general learning setting, which contains a surprisingly many like learning problems that we consider nowadays, which include regression and classification, all these supervised learning tasks, many unsupervised learning settings like clustering and density estimation, and it also contains a more modern type of machine learning problems like matrix factorization, matrix completion, and so on and so forth. But it does not include reinforcement learning and online learning, which is a primary focus of this lab machine learning group. Yeah, so it makes sense to formally introduce these notations for statistical learning. So this might be like very standard for most of you. So in the data domain, like it can be just like for unsupervised learning, it's just Z. For supervised learning, Z equals to a product domain of X and Y, and X is this feature domain, and Y is the label domain. And H is a pre-specified class of models that we try to that we are working with in this learning problem. And we also specify a loss function that takes a model and the data points from the data domain that gives you a real number that measures how well this model will predict for this particular feature label pair, or how much this model can represent the log likelihood of generating this data point from certain distribution class. Okay, and the risk, we defined it as the expectation, given any hypothesis within the hypothesis class, we define as the expected loss function. And the task of learning is to try to find H that minimizes the risk given IID samples from any distribution from this data domain. Question?
Sorry, I'm still thinking about this result you mentioned 2 slides ago about
Yeah.
the generalization. Can I ask
Yeah.
a question about that? So I think you were saying that if something's epsilon differentially private,
Yep.
the generalization error is at least epsilon? Is that what you said?
It's at most at
Oh,
epsilon.
it's at most epsilon.
Yeah, it's an upper bound.
Okay, that makes a lot
Yeah.
more sense.
Yeah. Yeah. So So let me now define what is learnability and private learnability. So for each learning problem, if there exists a learning algorithm A such that the output of A, this is the expected empirical risk. This is the expected risk of this output of this learning algorithm. Suppose it converges to the best possible risk that's representable within the class as the number of data points goes to infinity. We say that this problem is learnable. So there's a supremum over all distributions defined on the data domain. So this is like a uniformed requirement for learnability. Yeah, and it's agnostic learning because we do not require the data is generated from some distribution ahead of time. So private learnability is very simple. So the only thing we require is just an additional differential privacy constraint. Suppose a problem can be learned by any epsilon differentially private learning algorithm, then we say it is privately learnable. Like the requirement on epsilon is that it is just a finite number. All right. So so this is the entire class of problems in general, generalized learning, Vapnik's general learning setting. So what is previously known is that in pack learning, this is binary classification in discrete domains. So what has been previously shown is that any problem in the pack learning setting is also privately learnable. So the learnability of this class of problem is characterized by VC dimension. So this is basically saying that if you ignore the sample complexity, basically you do not lose anything with the additional constraint of privacy. So we show that in the more general setting.
Is there also general character? So
of rate?
For pack learning, we additionally know that empirical risk minimization is a general purpose algorithm that works for the entire class, right?
Yeah.
Is there a similar algorithm for private pack?
Yeah, you just try to privately minimize empirical risk.
What does it mean to privately minimize?
You try to come up with a solution that asymptotically minimizes empirical risk as n goes to infinity. Yeah, that's actually the very critical point because in the more general setting, we showed that the private learnability is characterized by the existence of an algorithm that can privately minimize the empirical risk as n goes to infinity. So the control. The control positive of this is just saying that something is not privately learnable if such a private empirical risk minimizer does not exist. Okay, so at a glance, it's hard to parse whether this is a positive or a negative result. So I claim that it's a little bit of both. So the good news from this result is that one can now just focus on finding a private empirical risk minimizer. And if this quest fails, then we can't find. If we can show that we can't find anything that's ERM and private at the same time, then the claim is that nothing would work under this strong notion of learnability. Okay, so we expanded a little bit on this good news. So and we come up with a generic algorithm for differentially private learning. So in standard statistical learning, the general algorithm is often to solve this regularized empirical risk minimization problem. And in order to make it differentially private, the most natural, arguably the most natural way of doing this is to sample from a posterior distribution rather than just minimize the regularized empirical risk. So there's a one-to-one mapping from this to that. So suppose we exponentiate the negative of this loss function, that will give us like an exponentiated Gibbs distribution that looks like this. And this gamma is just a weighting factor. As gamma gets to infinity, it becomes just empirical risk minimization. As gamma gets smaller, you get a more flatter distribution, and that gives you more privacy. And this pi can be just any prior that you can choose, similar to any regularizer that you can choose. So it's not hard to show that when the loss function is bounded, in this sense, then the posterior sampling algorithm itself is differentially private. Yeah, this is simply invoking the exponential mechanism by McSherry and Tovar, if you're familiar with it. But I just would like to highlight that this is actually a very strong assumption. Like suppose L is a 0-1 loss, then it doesn't really matter. But suppose L is something convex, like a square loss, then this is actually a very strong assumption on the boundedness of both the hypothesis domain and the data domain. So what we showed about this procedure is that it is 1 plus b over epsilon efficient. So this efficient is statistical efficiency in the sense that how much you can hope that it matches the Cramér-Rouault lower bound. So this says that suppose a non-private algorithm, the optimal non-private algorithm requires n data sample to learn this. A epsilon differentially private algorithm would require 1 plus b over epsilon times more data points. And this can actually be realized, like this sampling algorithm can actually be realized by something that's very similar to stochastic gradient descent. So there's this thing called stochastic gradient long-driving dynamics proposed by Radford Neal and Max Walling. So this is essentially simulating a stochastic differential equations, and this stationary distribution is just the exponentiated distribution that I showed you in the last slide, and we therefore it is differentially private asymptotically once the Markov chain mixes, and we also augment the result by showing that it is approximate differentially private if you just consider the algorithm alone, because it keeps adding noise to the gradient, and that noise alone actually allows us to state a approximate differential privacy result. And it turns out that the amount of noise you actually need to get approximate differential privacy is smaller than the amount of noise you need to add to make it a sampler. Okay, so in that sense, like this algorithm will give you differential privacy for free in some sense. And oh, it's epsilon delta differential privacy, yeah, for some small delta. And we also have another work published at Rexis that illustrate that this approach actually works really well on the Netflix data. This is one of the motivating examples that I mentioned earlier. And now we have a really system, like in terms of system, it's really fast, and it's also differentially private movie recommendation engine, and the code is available on GitHub.
So how does the gamma parameter feature in all of this? you have the gamma parameter distribution.
Yeah. Right? So the choice of gamma is basically epsilon over b. It's proportional to epsilon over b. So you can change gamma by you can adjust gammas to balance between utility and privacy. Yeah.
I was just trying to understand kind of the, I guess so you made some steps here. So you said that something is learnable, privately learnable if and only if there exists, or not if and only if, but if there exists private approximate asymptotic ERM.
Yep.
But the
this is just
serial sampling is not going to be
yes.
an asymptotic
Yes.
DRM unless you take gamma to 0 as a function of n or something in some appropriate way, probably, and need a bunch of other assumptions. So
not necessarily.
Okay. So
Because this L this L is getting larger and larger because this is the sum of all individual loss functions. Yeah. Yeah. All right.
So you're still assuming boundedness.
Yes. Yeah. For this asymptotic normality to hold, you do not need boundedness, but for differential privacy, in the more general sense, if you max over the loss functions, you do need this boundedness. Okay. Yeah. So and it's also deep learning friendly because it's just a minor changes from stochastic gradient descent. So there's also bad news from this theoretical result. So a lot of problems are actually not privately learnable. So the picture may well look like this. So one example of such problems that is not privately learnable is learning this threshold function in continuous domain. So you want to classify points on the real line between 0 and 1, and you want to learn a threshold function to do that. And this class of functions has VC dimension 1, so it can be learned excuse me, with a constant number of data points in the non-private setting. But in the private setting, for any epsilon that's finite, it's provably impossible to do this. This has a lot to do with the uniformity requirement of learning. Like suppose you relax this to like per distribution learning, then anything is learnable. But but for this, you can always construct an example where you need more and more data points to learn this problem privately. Yeah, for any finite epsilon. So it's really bad. Essentially, we can generalize this claim by saying that any loss functions that are discontinuous on the H argument will have the same issue here. So it really is a case that a lot of the learning problems are actually not privately learnable. So so the question becomes, are all learnable problems like epsilon delta differential privacy learnable? Suppose we relax the requirement to epsilon delta differential privacy. This, like intuitively, will have a lot to do with how fast we require this delta to go to 0 as n increases. So what we can show is that suppose this delta n requirement is relatively mild. Suppose it can go to 0 at a slower rate than 1 over n, then anything that's learnable in the general learning setting is also approximately private learnable. But that's really not the setting that we want to have, because we want delta to be cryptographically small, typically in differential privacy, because this allows us to just randomly output like one data point, and that satisfies this condition. So that's really bad. What's interesting is that using a recent result by Mark Bond, we can show that there's a sharp phase transition. Suppose the requirement of delta is on the order of 1 over n. So this is a setting where epsilon delta differential privacy marginally makes sense. Then even in that setting, the same problem of learning threshold function becomes hard for epsilon delta differentially private learning algorithm. Yeah, so that's really bad. So the story so far is that in general learning setting, although private ERM can learn all privately learnable problems, but many problems like classification, binary classifications in continuous domain are actually not privately learnable. And epsilon delta differential privacy does not resolve the problem. So the point is, even if a problem is indeed privately learnable, it does not mean that it's actually practical and people will use it in practical problems where you actually need privacy. So there are, in the past couple of years, I spoke to a lot of practical researchers, say those in U.S. Census, in government agencies, those who work in Australian Census, who try to actually privatize the data and serve the need of their data users privately, but they find differential privacy really frustrating for the following reason. Like often you need to add a lot, too much noise to the data or to the questions that people ask about the data set that results in really poor utility. And that also destroys the structures of the problem, say in cases of releasing a contingency table where you need every rows and columns to add up to the right number. And in order to make things to work in practice, there are a lot of hacks and tricks that you need to be aware of in order to do it. For instance, it takes us a lot of effort to properly do this clipping and rescaling of the loss functions in order to get this Netflix data to work with this differentially private learning algorithm. And what is worse is that it basically have a zero connection to the actual data that you have in hand. It is a worst case guarantee that protects the worst possible data set within the given domain that you can draw this data set. So it's a property of the domain of the data set rather than the actual data generating distribution. So that's really unsatisfactory from a practical point of view. So just to illustrate this with a simple example on linear regression, suppose like each user will give you a covariate and the response variable x and y, and we sample 100 of them from some distribution defined on some bounded domain for the sake of getting differential privacy. And the task is that we want to privately fit a linear regression of this form. So here it's just a simple two-dimensional linear regression, one-dimensional linear regression with an offset parameter. And in order to make it work, we also assume that beta 0 and beta 1 are within this bounded domain. Okay, so in this case, even though this is convex, it is also uniformly bounded from above, thanks to the boundedness. So the method we use is to just do this posterior sampling with an additional tuning parameter gamma. As I said, as gamma goes to infinity, this becomes ERM. As gamma becomes smaller, this is like you have more privacy. Okay, so this is what we get. Say, so the yellow horizontal axis is gamma. More towards the right, we get more utility, and more towards the left, we get more privacy. And the vertical axis can measure several different things. Say, on this green line, it measures the corresponding differential privacy epsilon that's guaranteed by this algorithm. On the other hand, this excess risk, it measures the actual utility of the problem, like how well you can minimize the excess risk with respect to the best possible linear predictor. Well, and because we actually generate the data, we can estimate the generalization by repeating the experiments again and again. And this blue line, it measures the generalization. So the theory doesn't break. Differential privacy epsilon would ensure the generalization to be at least at most epsilon. So it's an upper bound of this line. But the thing is, in order to make differentially privacy meaningful, epsilon needs to be relatively small. So a marginally meaningful setting is when epsilon is like 1. So in this case, you can know a little bit about someone, but you cannot know that with high probability. So anything that's above this epsilon equals to 1 would suffer from this exponential deterioration of privacy risk. So the corresponding utility on this problem turns out to be really bad. It's almost like 2 orders of magnitude worse than what suppose you do not do this differentially privately. All right. So So privacy community is aware of this issue, so that's why they come up with different ways to try to weaken differential privacy, including epsilon delta differential privacy, and more recently this concentrated differential privacy. But it turns out that none of them actually work too satisfactorily on the problem of learning. So is there some kind of much weaker notion of privacy that give you more utility in practice while preserving like the minimal kind of privacy guarantees that we can come up with? So this brings us our attention to the last part of the talk on this On-Avg-KL privacy. So this is how it is defined. Just a reminder that the definition of differential privacy looks like this. There are two supremum in front of the log likelihood ratio, and we want it to be uniformly bounded by epsilon. And On-Avg-KL privacy simply replaces the two supremum with two expectations. Okay, so in the differential privacy, the second part of this expression is a max divergence, and we just replace that with KL divergence. This is Kalbeck-Leibler divergence. Yeah, and the more critical thing is that is this On-Avg part that we are also taking expectation with two adjacent data sets that are drawn from the same distribution. So this notion of privacy, it measures the average privacy loss in the same sense of differential privacy, but it's just average over your output and over the data sets. It's not so much affected by pathological cases in the given data domain. It can be stated for every distribution separately, and perhaps more importantly, it can be estimated from data. So we now can estimate the lower bound of differential privacy from the data alone.
So it seems like if I have some sort of underrepresented population in my data, then this criterion makes it okay to breach their privacy, no?
Yeah, I agree. Like there are trade-offs. This is a much weaker notion of privacy, but still, the randomization is independent to any site information, so it protects against that. Yeah. So we showed that this new notion of privacy inherent a lot of the nice properties of differential privacy, including the group privacy and compositions. Suppose you have multiple data access, but now everything is in expectation. Like this actually subsumes differential privacy as a special case, because if this epsilon is upper bounded by, like this is always smaller than differential privacy. Suppose differential privacy epsilons hold, then this implies the composition theorem for differential privacy. It's also close to post-processing, and the thing is, we now do not need bounded loss functions to state any meaningful result for On-Avg-KL privacy. And when the loss function is bounded, the same algorithm that samples from the posterior distribution actually would guarantee differential privacy as well. So it's the same kind of randomness, but you just interpret it in a different way. That's more favorable in terms of utility. So what we can show is that suppose this is the algorithm that we are using. This is sampling from a posterior distribution with gamma equals to 1 and any given prior. Then we can show that our Avg-KL privacy actually characterizes the generalization. This is a slightly weaker notion of generalization with this expectation pushed inside this absolute value. Okay, but this is all you need in order to prove things in the statistical learning setting. Yeah, so this is like a strengthened version of the connection between privacy and the task of learning. And it's important that this result is stated for every data distribution separately. So a corollary is now that suppose you are doing any algorithm with this form, you can now estimate the generalization by estimating privacy, and estimate privacy by estimating generalization, as long as you rescale things appropriately. Let's just revisit this linear regression example. So where would this On-Avg-KL privacy lie on this figure? So this is where it is. First of all, let's look at this estimation of On-Avg-KL privacy divided by gamma. Not surprisingly, the theory it doesn't break. It estimates the estimated generalization error. These two lines are like essentially the same except for the randomness due to sampling. And on the other hand, On-Avg-KL privacy, it is like 4 times, there's 4 orders of magnitude better than differential privacy. And now, like suppose we just want On-Avg-KL privacy of a really strong average protection for a typical user of 10 to the negative 2, then the corresponding excess risk is as large as generalization. So you don't really lose very much, like if you assume a weaker notion of privacy. Yeah. So in summary, this On-Avg-KL privacy makes no changes to the algorithm. Its average privacy protection is practically more useful, even if the corresponding epsilon differential privacy has epsilon go to infinity. You can have meaningful privacy protections for the average users in your data set. And it characterizes the generalization for a class of algorithm that's posterior sampling. And I think it's a useful and necessary steps towards making private learning more useful in practice.
So are there problems which are not differentially privately learnable but are learnable under this notion of privacy?
Learning threshold functions is one typical example, but it's a little tricky because for On-Avg-KL privacy, the learning is defined for every distribution separately, and it restricts your algorithm. So it's not, yeah, it's a good question. I don't know the answer to. So I'm out of time, so I'm gonna skip most of the future work. But like this is more or less like trying to make use of On-Avg-KL privacy because we can now estimate it. We can come up with a private machine learning competition, just like the UCI data sets, so that people can now just run stochastic gradient descent, and because it's a randomized algorithm, and empirically evaluate how private it is. Like instead of going through all the analysis of getting epsilon and delta. And it's a valid lower bound for differential privacy as well. And what I'm planning to do in the near future is to use modern statistical tools to make differentially privacy more useful, and at the same time use privacy kind of ideas to help statistics and machine learning community to come up with more robust algorithm to selection. So this is an example of this New York City taxi data where we try to release this histogram of an hour's pickups and drop-offs. And this is a standard privacy release, differentially private release. Suppose we just add noise to every traffic junction with a Laplace noise. And suppose we just use a post-processing technique by denoising this output data over a graph, exploiting the fact that the underlying original data is is somewhat smooth. Then we can significantly increase the mean square error, improve the mean square error of this denoised DP release. And because it's just post-processing, you don't actually lose too much. And this is another thing that I've worked on in learning with on the aggregate information for the US elections. I'm going to just skip that. And this is the other part that we try to use randomization and privacy to solve the problem, to formally address the problem of p-hacking and selection bias. There are new settings, and we can pose a lot of theoretical problems and practical problems on this. A lot of these are all pretty open-ended. So I'll be happy to chat with you guys a little bit more on how we can collaborate on pushing this line of research forward. Yeah, it has a lot to do with online learning and sequential games. Yeah. So in conclusion, I just described in this talk the close connection between learning and privacy, and I come up with a new notion of privacy that gives you an alternative interpretation of the same randomizations that is needed to get differential privacy. And I'm like, this is an exciting field to be in, and I'll be looking forward to work with you guys to push this field forward. Yeah, thank you. Yeah.